Demonstrator 3 focuses on the development and implementation of a sustainable IoT node.
To show the potential of printed electronics in IoT, we developed a concept demonstrator, the all-printed IoT node, with the intention to set a benchmark for creating a fully printed IoT node using printed electronics technologies. The target level for functionality is to demonstrate on the laboratory scale that the technology is feasible and could be brought to higher technological maturity through development phases. The main focus of the project is the development and manufacture of thin film transistors and organic solar cell modules using printing technologies. The node receives data via an optical interface based on organic photovoltaic cells, which also provide the required power. The optical signals identify the specific node as well as function as a trigger. The nodes are hard-coded with an identity using optical filters integrated with the solar cell so that they respond only to specific light, red, green or blue. The output signal is a voltage pulse when the right node is addressed. Transistors and solar cells are made by printed electronics, the former by reverse offset printing for high accuracy and small dimensions using metal oxide active materials, and the latter primarily by gravure painting of polymers for precise layer control. The dimensions of the components are optimized to provide the required electronic function. Screen printing is used to create a plastic main circuit board where the all-printed transistor chips and the organic solar cell modules are integrated and connected together with the other components to make up the flexible printed node. The 5x5mm TFT chips are bonded to landing patterns in the base substrate using a flip chip style technique. The solar cell modules are attached to the base layout and connected to the contact areas. 3 modules are required and they are covered with optical RGB filters to hard-code the identity of the node. The proof of concept device has additional contacts to be used for circuit development and evaluation or testing. White LED lamps were used as a test light source, 1 for the clock and 2 for the address signals. The white LEDs are covered with the optical RGB filters and placed in a test chamber above the node. A signal generator is used to power the LED and an oscilloscope is used to track the output of the node as well as signals within the node circuit. Address 0 and address 1 were defined to be high, which equals a 1 when they are in the same phase as the clock, and low, which equals a 0 when 180 degrees out of phase. The access point is integrated into the existing Super IoT network, complete with back-end system and user interface. A Raspberry Pi single-board computer running Debian OS and Python script control the RGB lamps and handle the network traffic. The access point is controlled using a simple form over the internet. This proof of concept demonstrator shows that specific IoT functions can be implemented using simplified printed electronics-based nodes with improved sustainability and economics for mass production of nodes. In particularly for networks that require only a limited capability, but where there are concerns related to the environmental and overall cost.
By exploiting printed electronics technologies, we have created energy autonomous IoT nodes. These nodes have sufficient capabilities for selected use cases.